Okay, welcome to today's lesson. This is the last lesson in Unit 5, the last topic. Please make sure you get the Unit 6 notes downloaded from D2L for next week. We're going to be going through that unit rather quickly. This last topic is called the derivative as an instantaneous rate of change. And what that means is, if you read here carefully, in a case where the independent variable is time, and the dependent variable represents distance or position, and usually we use the letter S for that, for distance or position, then we can interpret the derivative of the instantaneous rate of change of the position function, that's S of t, with respect to time t. What that really means is this. If you're given a function for distance, or sometimes it's called displacement, and that's usually the letter S, if you want to find the velocity function related to this, well, the velocity, you can see right here, the velocity is just equal to the derivative of the distance, or the displacement function. Really what you're doing, if you think about some kind of a distance or displacement, let's suppose you have a length such as, I don't know, say kilometers. Okay, now that would be your displacement or your distance function. But when you take the derivative where the independent variable is time, what you're in essence doing is you're dividing it by a unit of time. So that could be kilometers per second, or kilometers per hour, per minute, or whatever. And if you take the derivative once again, guess what happens? You're dividing it by another unit of time. So the unit of time becomes squared. And if you look at this, those of you who are doing physics, that is acceleration. So what this basically means is, watch carefully. If you're given a function for distance, take the derivative once and you have your function for velocity. But if you take the derivative a second time, that's the second derivative which you looked at previously, then you get the function, or you get the equation for your acceleration. It's rather easy. It's rather simple. So let's have a look at some of the examples that they have here. This is on page 54 in your notes. And this example says find v of t, so that would be your velocity function, and a of t, and that would be your acceleration function, for each of the following position functions. So these functions represent position. You could think of it as distance if you like, or displacement. So here's the first one for a. S of t is equal to 48t plus 12. Well, the velocity function is equal to the derivative of the displacement function. So you just take the derivative of that function there, and you will have what? Let me see, 48t. Well, the derivative of that part is 48, and the 12 disappears. And there you go. So there's no variable, there's no t in the velocity function. And of course, what that means is your velocity is constant. It does not change with respect to time. Now, if you want to get your acceleration function, you take the derivative of the velocity function. Or, like I say, you can think of it as the second derivative of the displacement function. So you take 48, there's your velocity function. Take the derivative of 48, and by golly, you're going to get 0 because it's a constant. And that's exactly what we said just a moment ago. If your velocity is constant, meaning you're not speeding up, you're not slowing down, then it's obvious that your acceleration should be 0. Let's try the next one. S of t is equal to 4t squared minus t to the power of 4. So your velocity function, ladies and gentlemen, just take the derivative of that, and you're going to get 8t minus, okay, t to the power of 4. 4 comes down in front, t, subtract 1 from the 4, and you get t to the power of 3. There's your velocity function. And for your acceleration function, all you need to do is take the derivative of that once again. And you're going to have 8 subtract 4 times 3 is 12, t to the power of 2. And there's your acceleration function. It's pretty straightforward. There's nothing tricky about this at all. The last one on that page, again, you're given a displacement function, s of t. equals 3t squared minus 2t cubed. So your velocity function is only the derivative of that. So you're talking 6t minus 6t squared. That would be your velocity function, and your acceleration is going to equal, okay, the derivative of 6t is 6, minus the derivative of 6t squared, 2 6s are 12, t to the power of 1, which you don't need to write. And there you go. So that's how you get your acceleration and your velocity functions if you're given a displacement function. Okay, here's another example now on the next page. And let's read this one over carefully. Like I say, these are very straightforward questions. This one says, calculate the velocity and the acceleration of an object whose path is described by the function, and you can see it's a s of t, so it's your displacement function. They want the velocity and the acceleration at t equals 6 seconds. So not only do we need to find the function for the velocity and the function for the acceleration, but we need to plug in 6 into both of those functions. All right, let's go ahead. Let's play their game. So the velocity function is equal to the derivative of the displacement function. So all you're going to have is 40 minus 9.8 t. Okay, just t. Those of you who do in physics, by the way, that minus 9.8, that should kind of sound familiar to you. That's a certain constant, isn't it, in physics? And it's no coincidence that it pops up a lot in many of your formulas. That's the acceleration due to gravity. So there's your velocity function. They want the velocity at 6 seconds. We'll just work out d of 6. You plug in 6 into your equation, minus 9.8 times 6. This pen is awful. And so anyway, you plug that in, and you're actually going to get a negative answer here. Negative 18.8 meters per second. Now note the unit. I'm assuming meters, and well, I know it's seconds, but there was nothing really in the problem to indicate meters when they should have put meters. They should have had that there. So if we assume meters, we'll put in meters per second. It's important to put your unit there, by the way. And now we'll get the acceleration function by taking the derivative of the velocity function. The 40 disappears. And what else happens? All you have is negative 9.8. And actually, there's nowhere to put your 6, which means that your acceleration is constant. This appears to me to be a free-falling body? No, that appears to me to be an object that's been fired up into the air, and it's slowing down because of gravity. So anyway, there's nowhere to put your 6, so we'll just call that negative 9.8, and I'll put the unit down here, meters per second squared. Make sure you use the correct unit for acceleration as well as velocity. And there's another example here now, and this is actually the last example that they've got. This one says that a projectile is fired upward with a velocity of 44 meters per second. All right, so at least we know now that the displacement is in meters, time is in seconds. The distance s in meters above the ground of the projectile is given by the equation s equals 44t minus 4.9 t squared, where t is in seconds. Find the time when v is equal to 0. Now, this is a different question. This is not telling you to put in 0 for t. This is saying find your velocity function first, set it equal to 0, and what that will tell you, of course, is like at what time is your velocity equal to 0. And if you think about an object being fired into the air, the velocity becomes 0 at the very moment that it stops going up, and for a split second just stops moving altogether, and then starts to fall down again. And of course, that's also the maximum height. So let's get our velocity. Let's get our velocity. And so you're going to have 44 minus, and 4.9 times 2. There's that minus 9.8t again. All right. And what we have to do now is set this equal to 0. Set that equal to 0. So what you're going to have is 44 minus 9.8t equals 0. And that's a really easy equation to solve. That's just a linear equation. So you're going to have 44 equals, bring your negative 9.8 over, 9.8t. Divide both sides by 9.8. Like so. And of course they cancel. So you're going to get t is equal to, now I've got the calculation done already. It's approximately 4.49, and the unit for this time is seconds. So make sure again you put your unit down. So it's about 4.5 seconds. At about 4.5 seconds, the object reaches its maximum height and begins to fall back down toward the Earth again. Okay, now on the next page, that's the end of the examples, and there's the practice problems. I'll get you to try those for practice over the weekend. One question I want to point out for you, sometimes they are asking for the instantaneous velocity or the instantaneous acceleration, and that's where you would need your derivatives. But sometimes, look at question number 2, sometimes they ask for the average velocity, or it's even possible that they could ask for the average acceleration. Now, if they do that, that's not your derivative, people. That's not your derivative. Between t equals 5 seconds and t equals 6 seconds, well, what you would have to do there, you know your velocity equals your distance divided by your time. That's your velocity. Well, the average velocity between those 2 points, I'll just show you what the formula would be. You would have to basically do a calculation for slope, just like rise over run. Now on the bottom, think of your first t there. Think of that as t1, and think of your 6 seconds as t2. You would have to find the distance traveled at t2 minus the distance traveled at t1. Now you would get those by putting 5 and 6 into your distance function, into your displacement function, and then on the bottom it's just t2 minus t1. So it's like getting your rise over your run. That's what it's like. Distance on the top, time on the bottom. But for part B, where they're asking for the instantaneous velocity, now you would need your velocity function. Now you would have to take the derivative of the displacement function up there and plug 5 into that. So make sure you look at it very carefully. And the solutions, by the way, are all posted on D2L, the full solutions. So make sure you have a look at those. And that's it for today's lesson. Please try the remaining questions on pages 56 and 57. I don't think you'll find anything there like really tricky, but be aware of average versus instantaneous because they mean different things. Okay, so I'll stop there. Next week on Sunday, we'll be starting book number 6. We're going to be doing an assignment very, very soon on topic number 5. So you can get ready for that if you like, and I'll give you more information on that on Sunday. Okay, so anyway, have yourselves a wonderful weekend, and stay safe, be careful. Bye-bye.